Hello, everybody, and welcome back. We're on the third question of the 2008 Galois paper, and it's got 3 parts, A, B, and C. And what have we got for part A? It looks like they all involve this chart here, although in the last one, the chart doesn't actually have some numbers for number of students who answered correctly. Well, we'll get into that. So, 3A. A class of 20 students was given a 2-question quiz. The results are listed below. So we had 2 questions, questions 1 and 2. 18 students answered the first one correctly. 14 answered the second one correctly. Determine determine the smallest possible number and the largest possible number of students that could have answered both questions correctly. Explain why these are the smallest and largest possible numbers. Okay, so there's some ambiguity, there's some overlap, and depending on your background, you might do this one of, I think, 3 ways. Okay, you might just sort of write a whole bunch of text and reason your way through this one, and if you can do that, that's fine. As long as you're clear when you're writing these things out, no problem. Another group of you might have been raised on certain problems like this and been trained to do Venn diagrams. I've done some questions similar to this in the past with Venn diagrams, and Venn diagrams can be great. A lot of people understand how to read Venn diagrams, and it's great to visually present your information that way. A third way, which is the way I think I'm going to do this one, is with a counting tree diagram. Okay? Now, if you're not familiar with counting trees, because I don't believe they're part of the curriculum exactly, counting trees is a way to organize information. I find it's a little clearer than Venn diagrams. It depends on sort of what day. Okay, but you might have sort of. So we might write a counting tree for first question and second question, and the way we break down our information is. I'll write Q instead of quest. The way we break down our information in a counting tree is we sort of have branches for different outcomes for the first question. Now, the first question, either students got it correct or not correct. And then for the second question, students either got it correct or not correct. But in this way, I can break down my information, and if we follow along a path, we get the students who got the first question correct, but then who got got the second question not correct. Okay? And we label these with numbers, so we know 18 students got the first question correct. How many students got the first question not correct? Well, there's a total of 20 students, so there's 2. And the sum of the numbers that we place on branches always equals the number that went into. So we go into C, the numbers coming out of C have to add up to 18. Okay, and as long as you understand that, or as long as you can explain that, you can use a counting tree, and I'm going to try and use it this question. If you did this one with Venn diagrams, great. If you struggled with this one, try and understand the counting tree as we go along, and if you did it with Venn diagrams but you don't understand counting trees, watch and see how I do this, and decide for yourself, maybe this might be an easier thing, and maybe it's something to look into. But I do a lot of these questions with Venn diagrams. I wanted to switch it up, at least once. Okay. So we can start filling these things in. So 18 got the first question correct. 2 got the first question not correct. Now we also know that 14 got the second question correct. So do I just put 14s here and here? Well, no, and stop and think about that. This doesn't make sense. How can 2 and 14, you'd have to have negative 12 students get it not correct. So with further branches, the number of people who got the second question correct, so they could have gotten the first question correct and then the second question correct, or they could have not gotten the first question correct and got the second question correct. So we might label these numbers A and B. A plus B has to add up to 14. That's the total number of people. Okay? And if you think about it, We know 14 people got the second question correct, so we need the numbers adding that lead into second question correct, that C in the second column. We need that to add up to 14. But we've broken it down. We've got A of them, let's say, 6 of them. 6 of them got the first, are part of the 18 who got the first question correct. And those 6 also got the second question correct, and that would tell me then 12 people got the first question correct and the second question not correct. And things like that. So you get the same sort of representations you would with a Venn diagram. I just find the tree diagram a little easier to read. Not always, and I know I'm not alone in this, but I know it's not everyone who agrees that tree diagrams are better than Venn diagrams. But having just finished teaching a course on finite math where we don't use Venn diagrams at all and use tree diagrams, it's a useful skill. Okay. So here's where we get a little wiggle room. Okay. So we can say there must be 2 people here, and I would explain that in my little tree diagram. 2 people must have gotten the first question wrong. And so B has to be between 0 and 2. A has to be between 0 and 18. But we also know that B has to be between 0 and 14. A has to be between 0 and 14, because at most 14 people got the first question correct. So this tells me A has to be between 0 and 14, and combining these two, B has to be between 0 and 2. So, filling in these numbers, let's identify what we're looking for. We want the what was it? Smallest possible number and largest possible number of students who could have answered both questions correctly. So, where are the people who answered both questions correctly? Answered correctly, and then A. So, A is the number who got both correct. Okay. So what can A be? Well, A could be at most 14. But could A be as small as the 0 we've got here? Not quite, and we'd need to explain that. If A were 0, then B would have to be 14, but B is at most 2. So what we can say here is, since B plus A is 14, 0 is less than or equal to 14 minus A, which is the same as B, less than or equal to 2. And now I can rearrange this and add A to both sides. So A is less than or equal to 14, less than or equal to 2 plus A. And I'm running out of space, so let's move over to the next side. So A is less than or equal to 14 is less than or equal to A plus 2. Taking these two, 14 less than or equal to A plus 2, 12 is less than or equal to A. And we know A is less than or equal to 14. A is at most 14 and at least 12. So at least 12 people got both questions right. Okay. Now, how do we know this is true? Because didn't you just have an inequality here that said A could be at least 0? How do you know 12 is right? How do you know 14 is right? Well, we can double check them by filling in a tree diagram that makes sense and has these numbers. So 18 here, 14 here. So that would mean 4 got the first question right but didn't get the second question right. And we'd have 2 people got both questions wrong. Nobody who got the first question wrong got the second question right. And this all works out. 18, we could have 12 up here, and that would leave 6 down here. We'd have 2 down here and 0 down here, and it all works out. But notice if we tried to do something like 18 and 11, yeah, you can put the 7 there, But then this would have to be 3 in order to make these two add up to 14. But then you'd need -1 here, and something's gone horribly wrong. Okay? But rather than just try drawing a bunch of tree diagrams and saying, well, these are the ones that work with the most extremes here, we used some inequalities and got a nice little answer here. Okay? And, add in a sentence or two of explanation. I've done it all verbally because it's a video, but do that and you're just fine. Now, let's move on to B part. A class of 20 students was given a 3-question quiz. Okay, so I'm picturing a bigger tree diagram. And this is one of the advantages I think tree diagrams have over, say, Venn diagrams. A 3-intersection Venn diagram is a little fiddly, but a 4-intersection Venn diagram, it's not very easy to draw that. You have to, well, actually, it's quite interesting to look into generalizations of Venn diagrams beyond 3 intersections, because you don't get nice circles for all of them. Okay, whereas a tree diagram, you can just keep branching and branching and branching and branching. And that's a nice advantage that tree diagrams have. Alright, so 20 students still, 3-question quiz. Here are the results. Determine the smallest number and largest number of students that could have answered all 3 questions correctly. Explain why these are the smallest and largest. Okay. So let's get a bigger tree diagram. So first question, second question, third question, correct or not correct? Okay, bigger tree, but it's still very easy to follow along as long as you read off branches. Now, what number are we most interested in? People who got all 3 correct. So we just sort of follow along. And so the number that we want will be placed here. So let's call that A again. So we want to know how big A can be, how small A can be. How big or small can A be? That's the question. That's what we need to work out. Now we can start filling this in. 18 people got the first one right. And that tells me that 2 people got the first one wrong. Okay. Now 14 people got the second one correct. And 12 got the last one correct. So, we might have some numbers B and C here. B plus C has to be equal to 14. We've got A here. We might call this D, E, and F. A plus D plus E plus F has to be equal to 12. Okay. Now we might be able to start making some inequalities. We can even fill in some numbers. Like this is 8. This has got to be 18 minus B. This has to be 2 minus C, and so on. And you can fill some very intricate numbers in. But I think we should just probably start to reason. And do our best to just sort of reason a little bit. So A can be no bigger than B, which has to be at most 14. But from this thing right here, A is at most 12. So I ask myself, could A actually be 12? It's possible. It's certainly possible. And then what else could we have? Well, C is at most 2. And so B is at least 12. But maybe all 12 of those go here. So we have to ask ourselves that. And then A could be 0. Is that possible? Not quite. If you look back at our previous pictures, you'll notice that these numbers add up to the number of students. These numbers add up to the number of students. So you're going to also have to add up to the number of students. But A, D, E, and F already add up to 12. So this has to be at least 8. So that means I think A has to be at least 4. But let's write it up a little bit. So A is at least B, which is at least 14. But A, well, A is at least 12. Can we make a so as soon as you get an inequality that says, A is at most 15, if A can be 15, you would be able to make a tree. That's sort of how you prove it. Can we make a tree with A equal to 12? 18 and 2. So I want this to be 12. I don't think this will be that hard. I don't know, make B 12. It doesn't really matter. 2 here, 0. Let's say a 2 here, 0, 0, 0, a 0, a 0. Oh, sorry, this should be a 6. And I don't know, 3 and 3. It doesn't really matter. But we can fill it in, no negative numbers anywhere. Whereas if I tried to do something like, can A be 13? Oh, sorry, we need, it does matter, it does matter. I was wrong, because I have to remember that these ones here have to add up to 12. So I'd have to put a 0 here and a 0 here, and that would make this a 2, and that would make this a 6. But other than that, that's fine. But as soon as I put a 13 here, one of these has to add up. One of these has to be negative in some way. Otherwise, the ones that we had labeled in, I guess, purple don't add up to 12 unless one of them is negative. So there's sort of that. So A can be at most 12. There's our reasoning there. Now I think the harder one to reason out is what is the least A can be. Okay. So A is at most B. B plus C is 14. So B is 14 minus C. C is at most 2. So B is at least B is at least 12. Sign flips around. Okay. Now if I draw my picture again, so there's B, there's C, there's A, D, E, and F. And they're the ones I'm gonna try and always mark them in purple because they have to add up to 12. So I'll remember that. But so B is at least 12. Let's call this guy G. A plus G must be B. So A plus G is at least 12. Okay. Now A plus D plus E plus F is equal to 12. Call this G, H, I, and J. G plus H plus I plus J. It has to be equal to 8 because the whole column has to add up to 20. So G is at most 8. Therefore, A is at least 4. Because we know A plus G has to be at least 12. Take away 8 from both sides, assuming that G somehow reaches its maximum. A has to then be at least 4. Maybe it can't be. Maybe there's something else that forces A to have to be at least 6, but here we go. We've got some reasoning. Can A actually be 4? Because if it can't, then we know A has to be a little bigger. So let's try and fill in a tree diagram. 18. We'll make B 12 here to be as small as possible. So now those two add up to 14. Fine. Can A be 4? Well, that would make G 8. And that would mean the rest of these all have to be zeros here. Then this is going to be 6. So we'll put a 6 here, a 2 here, a 0 here, and a 0 here. 4 plus 6, let's just make sure my numbers add up to 12. 4 plus 6 is 10, plus 2 is 12. Everything worked out. And we have no negative numbers. So A is at least 4. And remember, A was correct, correct, correct. All 3 correct. And that's the number that we were looking for. Okay. You might ask, could it be smaller? Well, then we'd need to have something like this is 3, but then that would bump G up to 9. And there's no way that, because once we have 9, then my purple lines can't add up to 12, because the whole column has to add up to 20. And if 9 of them are already accounted for on a non-purple branch, you're going to have at most 11. So, no, it can't be 3. Nifty. All right. You might be able to tell I don't have a lot of practice explaining the tree diagram ones in videos, so this is a learning experience for me as well. C part. A class of 20 students was given a 3-question quiz. The results are listed below. 1, 2, 3. And here we go. X, Y, and Z we don't know. Where X is greater than or equal to Y is greater than or equal to Z, and their sum is greater than or equal to 40. I bet that'll come into it at some point. Determine the smallest number of students who could have answered all 3 questions correctly in terms of X, Y, and Z. Fine. Okay. So we'll make another tree diagram, and we'll once again mess about with some inequalities. I don't feel the need anymore to write C and not C, but I guess I'll write it because, I'm presenting, and because you should write it so that your diagrams are clear. And let's make our diagrams clear by not having overlap. So we'll put not C here, C, not C, C, not C, C, and not C. And you should label the top first question, second question, third question. Okay, once again, we want the students who got correct, correct, correct. So we're interested in this. I'll call it A again. Okay. So I know that this number here is X. I'll call these guys B and C. B plus C must be equal to X. This here must be 20 minus X. So that tells me C is at most, so B here then is X minus C. I'm just sort of remembering, well, what did I do in the last question? Because the last question was 3 layers. And the last question, well, I'm trying to figure out how big and small A can be. And what did I do? I messed about with B and C. I rearranged and let B be 14 minus C. Well, in this case, it's going to be Y minus C, and so on. Oh, it's Y, not X. Silly me. So Y, so this is Y minus C. Now C is at most 20 minus X. So that means B is at least Y minus 20 minus X, which is X plus Y minus 20. Now, here's me worrying, is X plus Y definitely greater than 20? I don't think I can... Oh, yes, it would have to be. I'm just going to write that off to the side. X plus Y plus Z is greater than or equal to 40. X is greater than or equal to Y is greater than or equal to Z. So... X plus Y has to be greater than or equal to 40 minus Z. But 20, because there's 20 students in total. So Z is less than or equal to 20. So x plus y is in fact greater than or equal to 40 minus 20, which is 20. Okay. That's allowed. No negative numbers, don't have to worry about that. Although that wouldn't really be a problem, that would just mean b can be at least 0. But, okay, fine. So now I know b has to be between x and x plus y minus 20. Whatever that might be. And again, y is less than or equal to 20, so this is definitely going to make x plus whatever it is less than x. Less than or equal to x. Okay. Fine. What else did we do? Let's get our purples out and label. So the purple lines have to add up to z. We'll call this D, E, and F. And since I think I know where this is going to go, we'll call this G, H, and I, and J, since we had to use those last time anyway. Okay. So, A plus D plus E plus F must be equal to Z. And that tells me G plus H plus I plus J must be equal to 20 minus Z. Fine. Okay. Now B plus G, A plus G is equal to B. Okay. Now A is less than, so this one right here tells me A is less than or equal to Z. I think the best A can be is Z. And that's the maximum. We'll draw a tree to prove that in a moment. But let's get close to that minimum. So A plus G is equal to B. But this line here tells me G is less than or equal to 20 minus Z. And combining these two facts, we get A is greater than or equal to B minus 20 minus Z. Now we want A to be as small as possible, so we'll use the smallest possible B, which will be x plus y minus 20, minus 20, and it'll be plus z. So A will be greater than or equal to x plus y plus z minus 40. And again, that's fine because we were told x plus y plus z is greater than or equal to 40. But this should be the small. This corresponds to our A has to be at least 8, or A has to be at least 4 from the previous question. Because 18 plus 14 plus 12 minus 40 is in fact 4. So this, I like the fact that they gave us B, which was essentially the same question but without the x, y, and z. So now I can check my numbers. Yeah, 18, 14, 12. Oh, look, A is at least 4. A is at least 4, and A is at most 12. Well, we learned that in the last question. So, these are our answers, but we haven't proved them. We just have a bunch of inequalities. There is no way you can say, well, there's no way, there isn't going to be another inequality that comes along that revises these. These inequalities are true. The only way to prove that these are the max and min is to actually construct trees. So, and I would definitely write that I need to construct trees. It shows that you know that it's not all about inequalities. Construct trees to prove these are the biggest and smallest. Okay. It's sort of like if somebody came along and said, well, I've got a proof that human beings will never, will always be less than or equal to 5 meters in height. Okay, but that doesn't prove that the tallest a human will ever be is 5 meters. Because somebody might come along 20 years down the line and do some more research and say, well, actually humans can only be at most 4 meters in height, no matter how much evolution we go through. Okay? So there's a difference between saying, yeah, it can be at most this, and actually saying, and the maximum is realized. And that's what this question's after. It's not, obviously I could say A can't be more than 21. A has to be at most 20. But there are other factors that are constraining it a bit. You'll never actually see 20 people get all 3 questions right. We know that won't happen. Okay? But there is that inequality that says A has to be less than or equal to 20 just because there are 20 students. So you have to go along and actually show, does this happen? Is there a tree diagram that does this? And so we'll do X. We'll call this, we'll say this is Z. 0, 0, 0. We'll say that this is Y, so this is Y minus Z, which is positive. Okay, to show that this works out, you have to actually show that these other lines aren't going to be negative, and I think that's the challenge. So we know Y is less than or equal to Z. We'll call this X minus Y, and we know that that's positive because we were told X is greater than or equal to Y. Let's see, we have 20 minus X, which again we know is positive. 20 minus... Oh no, sorry, this will just be 0. This one will be 0, this will be 0. And this will be 20 minus X, so this will be 20 minus X. With those zeros there, and then... so I'll just make a comment. 20 is less than or equal to X. Therefore, X is less than or equal to 20. So that tells me 20 minus X is greater than or equal to 0. And then what will we have here? We'll have X minus Y here. And then this column does indeed add up to 20. 20 minus X plus X minus Y plus Y minus Z plus Z is in fact 20. Great. But more importantly, all these numbers are non-negative. So this does work. All numbers in the tree are non-negative. So this is a valid tree. Okay. Now for what I would say is the harder one. I need a bit more space. Okay, 20 minus X, again, that's fine. So we'll give it a little check mark. We wanted C to be as big as possible, and that means that B is as small as possible. And this will be 20 minus Y. Again, that one's perfectly fine. That's allowed. So we'll put 0 here. That'll make both of these 0. Now we want G to be as big as possible. So, and we want A to be 20 plus, X plus Y plus Z minus 40. And that'll mean that this is 20 minus Z. And that's allowed. And that'll mean that the other numbers on the bottom rows will have to be 0. So that'll mean this is 20 minus X, and this is 20 minus Y. Again, these numbers are all fine. So is this one. These are all non-negative numbers, and we're done. But you can't just say, oh, here's a tree, I filled it in with a whole bunch of variables. You got to point out all these numbers are non-negative. So this counting tree is valid, and that tells me that yes, the minimum that I realized, or that I mentioned earlier, is actually realized in nature, in a diagram. Okay, so that question was a bit of a mess. I mean, it's a fine question. I think no matter what way you do it, you're going to have a lot of explanation on your hands. I think a tree diagram or a Venn diagram, if you're more comfortable, goes a long way to earning marks on this because it makes things a little clearer. I mean, you could just give paragraph after paragraph of reasoning, but it'll be hard to follow. But if you have a tree diagram, you know, it's a little bit better, or a Venn diagram. But there's a lot going on, and hopefully I explained it well enough. I maybe didn't write enough sentences in my actual written stuff, but verbally I think I did okay. But we've got one more question to go, and that's question number 4. I will see you for that in the next video. Until then, have a wonderful day.